Hi, welcome to the second part and the third tutorial of the SIDD online tutorial series. In this tutorial, we'll be walking through how to alter the model code in order to analyze the effects of the policy counterfactual that is described in tutorial 3.1. So in tutorial 3.1, we define the subject for analysis. In this tutorial, we'll be altering the model code, and then as soon as we've altered the model code, we can go on to use the model to generate data for policy counterfactuals and then to analyze those data in order to undertake the analysis that was defined in the first step. Sometimes it won't actually be, or very often, it won't be necessary to alter the model code in order to explore a subject of interest. One of the reasons that this particular analysis is useful for the current purpose is that it does involve some variation of the model code. And so by walking through the analysis, you should hopefully get an idea of what altering the model code involves. Furthermore, the code that's altered is really fundamental to the model's use of the life cycle framework to project behavior through time, and so that gives another reason that that this is a particularly useful analysis to consider here. So recall from the preceding section 3.1 that we're interested in three alternative behavioral assumptions. One in which the functional description of behavior is assumed under the base policy environment remains unaltered under the policy counterfactual. Another in section 3 where both savings and labour supply respond optimally to the policy counterfactual, and then an intermediate in which labour supply responds optimally but savings does not. So to capture these behavioural alternatives, it's necessary to understand exactly how it is the model works, how it generates decision making. Now, for the purposes of this study, we'll be limiting the agent heterogeneity, or individual-specific heterogeneity, to the 14 characteristics that are defined in the table up here. All those characteristics with an asterisk are assumed to be affected by some form of uncertainty. And all others are projected through time in a deterministic fashion. So we've got mainly demographics, savings, and wage potential as the key sets of characteristics to be considered for analysis. Now, when the model comes to generate a population cross-section through time, it does this in two key stages. In the first stage, it solves the lifetime decision problem using dynamic programming methods. And in the second stage, it projects the population through time based on the behavioral solutions obtained in the first stage. So let's provide a diagrammatic representation of actually how the model simulates behavior through time. So the model begins right at the very beginning. The model begins by overlaying all feasible combinations of individual specific characteristics with a large grid, a matrix. And here we have a matrix represented with 3 dimensions, with age going up the sheet, wealth going into the sheet, and wage potential going horizontally across the sheet. So we assume that this matrix overlays all possible combinations. In our context, obviously, we would have a 14-dimension matrix, recalling that we have 14 individual specific characteristics to worry about. Here we're stylizing that with just 3. Now, to solve the lifetime decision problem, the model begins by considering all of the intersections in the very oldest age that is feasible within the analytical context. So, in our analysis, in our applied analysis, we assume a maximum potential age of 130. Not everybody will live to age 130, obviously, because many people die before that age. But it's a maximum a potential age of life. And it considers each intersection in this final period of life, if you like, and it solves the lifetime decision problem for each of these intersections. Now, note in this period of life, there is no future because everybody knows they're going to die with certainty. So uncertainty disappears. It becomes a deterministic problem. It's very easy to solve using, your standard intermediate micro economic, methods of analysis. Having obtained solutions for all of the intersections of this final period of life, the model saves all of the decisions, all of the optimizing decisions, and importantly, it also saves the optimized measures of utility in that final period of life. It then steps back to consider the same solutions for the penultimate age of life. Now here, the utility maximization problem must take into account not only utility in this final period, this penultimate period in life, but also the bearing that decisions have in this period on the likely location that individuals will be in this final period of life. Now, and the bearing that that location has on utility. So, for example, take this individual here. Let's say this individual chose to consume as much as they possibly could in this period of life. Well, that would put them here in this grid at effectively zero wealth. They would be here, and that would be associated with some level of utility. And so when evaluating whether consuming as much as possible in this period of life was a worthwhile idea, you would be trading utility here for the fact that you get a high utility here for the fact that you get relatively low utility here. And so you would sum that utility up using the intertemporal form assumed for the utility function, and that would give you one plausible decision alternative. And then there are numerical routines within the model that then you undertake a search over the feasible decisions at this period of life, taking into account the bearing those decisions have on the final utility in the final period of life to identify a lifetime optimum for utility. Having defined the lifetime, the decisions that maximize lifetime utility in this penultimate period of life, the model again saves both those decisions and the form of expected lifetime utility, and then proceeds to consider decisions in the next preceding period of life. Note that when the model is evaluating expectations concerning utility in the final period of life, if a particular considered decision in the penultimate period implies a position in the final period of life that is off a precise grid coordinate, then the model uses interpolation methods in order to approximate utility in the final period of life by drawing on nearby grid points to obtain that approximation. Furthermore, if there is some uncertainty associated with the final period of life, where precisely an individual will end up in the final period of life, then the model resolves that uncertainty by associating each plausible alternative with a specific measure of probability, and the assumption of von Neumann-Morgenstern preference structure allows expected utility to be evaluated as the form of a weighted sum. In the case of human capital, or wage potential, which is assumed to vary, to be uncertain in a continuous fashion, subject to a log linear distribution, the model uses a method for approximating the expectation of the probability using a discrete set of ordinates defined by the Gauss-Hermite routine. So quadrature. So basically, solutions are obtained at all intersections in the final period of life, and then backward induction is used to obtain solutions in all preceding periods of life at all grid intersections. So with a full set of solutions, basically this grid then acts as like a lookup table in order to identify the behavior of individuals when projecting them forward through time. So let's consider that case. So now we have a complete solution to the lifetime decision problem. Basically, each intersection of this grid has stored the optimizing decisions and the optimizing measures of utility. And in the applied context, for example, that we're considering here, this grid comprises some 200 million individual intersections. It will comprise more or less depending upon the way that the model is set up. But in this context, 200 million, so it saves that data. And then when it comes to project the population through time, basically the reference population cross-section is located within the grid. This individual, for example, might be age t-2, and they have this particular measure of wealth here, and they have this measure of wage potential, so that puts them here. And similarly, for all of the blue people here that are represented in the reference cross-section, if we consider, for example, just those people at the youngest age, then what the model does is says, okay, for this individual, their decisions implied by this grid coordinate that they're closest to, again using interpolation methods wherever an individual that is not located precisely on a grid, their decision would be to consume a certain sum, let's say £350 a week, and to work full-time, let's say. And given those decisions, and all of the other processes that are assumed to govern intertemporal transitions, we can project those individuals forward through time. Now, some of the things that are projected forward through time are associated with uncertainty, as was noted in the preceding slide, all of those characteristics associated with an asterisk. Wherever a characteristic is associated with uncertainty, a random draw is taken in order to project them forward through time. And so a set of random, each individual is also associated with a full set of random draws. You project them forward through one period of time, and that process can be repeated into the future to project them throughout the life course. So this grid, the lifetime decision problem, the life cycle model, the bearing that the life cycle model has within this SIDD micro simulation model is entirely encapsulated by this grid structure that I referred to in the preceding slide. And it's that grid structure that we need to adapt in order to capture these behavioral alternatives that are the focus of interest here. So basically, we have three alternatives. One, the case in which savings and labour supply are assumed to respond optimally to the policy counterfactual. Now, this is the default simulation approach for this model structure. So actually, this didn't require any kind of reprogramming or any adjustment. It was just a standard model projection. A second, where functional description of behavior remains unchanged relative to the base policy environment. This is really easy to implement within this structure. Hopefully you can see. Basically, all we needed was to ask the model to use the grids evaluated under the base policy environment when projecting the population through time in context of the policy counterfactual. So basically, we just loaded in the base grids, the grids for the base policy environment as the basis for projecting behavior under the policy counterfactual. So that's that captures the second alternative. Now, this third alternative actually required in which labour supply responds optimally to the policy counterfactual, but savings behaviour remains functionally invariant, required a little bit of reprogramming of the model, and it's that reprogramming that we'll refer to in this tutorial. And by doing so, you will hopefully gain an appreciation of where the optimizing routines are and how this grid structure is actually appearing in the model structure, so that you can adapt these things for your own purposes. The materials to this tutorial include a job file and an edited source file folder, and in the edited source file folder you'll find some Fortran files which provide all of the code that was altered in order to implement the behavioral alternative that is one of the focuses of the interest of interest in this tutorial. Now, it's beyond the scope really of this tutorial to provide a detailed walkthrough of the source code to the model. The source code of the model extends to tens, if not hundreds of thousands of lines of code, and it's just beyond the scope of a tutorial to walk through that. For the moment, however, it's useful to discuss the steps that I suppose I usually implement when I'm working on introducing a new feature or functionality to this model. And the place that I normally start is the Excel file. So basically, I'll set up altered parameters. And then I'll start working with the source code for the model. So let's have a look at the change that was made to the Excel files in order to implement this behavioral alternative that we're interested in here. Basically, the only change that was made was to implement a new switch. So basically, you can see highlighted in yellow in the job file that is included as part of the source code, as part of the materials to this tutorial. Columns X and Y, row 17 of the input sheet, but it also applies to the input A sheet, is this IMA conference, exogenous assume consumption and pension participation. So basically, this is a switch that will exogenously assume consumption and pension participation by the model when it comes to optimize decision making in the first stage of the model projection. That is where it's solving the lifetime decision problem. By default, that's set to 0, so the switch is turned off, and so this model should generate results under that context that are identical to the case in which no changes were made at all. And it's switched on when it takes any other number. Usually I set that number to 1 when I turn it on. Now, it's in order to so this number will automatically be loaded in to the model as part of all of the parameters that are loaded in at the initialization stages of the model code. In order to track it down, there are these comments at the very top of each of these columns here. If you double click on one, you can open the box up, and you probably can't see it in the video, but here it says model underscore par. So this vector here refers to is referred to in the model as model underscore par, and it emits, the model doesn't load in the first column of the spreadsheet. So this would be row 1 of model underscore par, and this one here would be row 16 of model underscore par. So that's the switch that controls whether this functionality is turned on or off. So let's have a quick look at the code, just to give you a very quick overview of how this thing actually is put together. The code is what they call a mixed code, in the sense that it includes elements of Fortran, C++, and C# in it. The C# is used for communications with Excel. In the past, we had implemented direct communications between Fortran and Excel, but these were very fragile, in the sense that whenever there was an update, either from Microsoft side or from Intel side, we would find that the Excel communications could break down. So to minimize those problems, I suppose, what we've tried to do instead is implement communications through C#. Now, for those of you who are not familiar with C#, C# is like Microsoft's version of Python, if you like. It's what they call I think it's a high-level language, low-level language. I always get mixed up. Anyway, it's a language that allows you to get a lot done with just a few lines of code. So there's a lot of pre-packaged stuff built into C#. Now, C# is easy to communicate with via C++, and C++ is easy to communicate with Fortran. So we use C++ as like a bridge between Fortran and C#, and that's what all these, if you look in the Solution Explorer, I'm not sure you'll have Solution Explorer in your version of Visual Studio already observable. If you don't, you can just go View and Solution Explorer. In any case, mine is here. You can see the Fortran code here. Comms refers to communication routines, especially with Excel, really, but also with CSV files, to save CSV files. And taxes is where all the taxes are kept. You don't get this whole package provided with the model by default. You have to apply for the full set model source code separately by email. That's really just to avoid, you know, sort of abuse of this facility. But otherwise, you know, it's freely available. And the main model code for SID is in this this Fortran code here. So this is the C#. There's a C++ wrapper. You don't really need to know about this stuff. C++ static is the C++ DLL that that Fortran is communicating with, and then SID here. So if so ignoring, you know, all of these others here, if we just get straight into SID, the SID model is sort of organized in an hierarchical sort of structure. It starts off with the master routines, and then it typically works its way down through all of these files here. Each file sort of deals with a different issue, and within the files are modules, and within the modules are subroutines. As I say, I can't go through all of this stuff in this tutorial. It would just take too long. For the moment, I think what we'll do is we'll focus on just those aspects of the code that required some adaptation for the current policy scenario. So the place where the grids are actually set up is in this axes_init file. Now, what this does is it initializes the axes for the grids. You'll recall from, you know, the PowerPoint presentation that I just went through, that there's a large grid that overlays all feasible combinations of individual specific characteristics in the model. The grids for that axis, the axes for that grid are defined by this routine here. But the calculations for the analysis are actually only undertaken, you know, in routines here. Now, that you'll notice that some of these source files are turned off and turned on, depending upon the you know, the build variant you use. So there's only one platform in this model. It's a 64-bit platform version. If you use an MPI variant, then you will see that a couple of files are turned on and a couple of files are turned off. Basically, for those of you who are unfamiliar with MPI, MPI is a parallelization that is designed for supercomputing, in you know, simple terms. So it's it's a parallelization that is designed for distributed computing framework, involving worker nodes and header nodes and so on. Mostly when you're working on dedicated workstations and that sort of thing, you don't need the MPI enabled, because the model includes both parallelizations in design written in MPI and parallelizations written in something called OpenMP. And OpenMP is sufficient to efficiently take to utilize your computing resources on a dedicated workstation. So that's just a small aside. And I said it because the grids are actually evaluated and managed in this block of code here, sort of, you can see grid manage 2, basically grid manage 1, just sort of, you can see the comments here, but effectively it sort of sets up the looping structures and makes sure that this grid can, or this model structure can reasonably be solved on the computing hardware that you have access to. And then this one actually goes ahead to try and solve a particular grid structure. And so it's really here where recall that the alternative that we needed to amend the source code, the model source code for, was the case where labor supply responds optimally to a counterfactual, but consumption and savings behavior in general remains fixed as it was under the base policy structure. So in order to do that, what we need to do is first of all load in the solution, the grid solution, under the base, and then deliver the solutions to consumption and pension participation that were obtained under the base and impose those as a constraint when the model comes to optimize utility in context of the policy counterfactual. And so all the model will then do is optimize with respect to labor supply. And so that will just involve a little bit of adaptation of this model structure here, but otherwise the remainder of this code remains invariant as under the base specification. Please recall that that the model version considered here is 3.16, and so basically you should make comparisons with 3.16 regardless of which version is most recent at the time you look at these tutorials. So the edited source code, as I say, is in a folder here, and it's useful for us to try and compare these files against the default files that the model comes supplied with if you go through the application process. And so basically, I'm not sure whether you have access to this, but if not, you can download it freely from the internet. It's called WinDiff, and it's a very useful tool for comparing differences between text files. And here we want to compare the differences between the files that are in this edited source and the files that are provided with the model by default. So to do that, it's really quite straightforward. We'll compare directories. So we'll go here, say File, Compare Directories, and then we'll put in, I've already put in the edited source and the source file, and we hit OK. And then the model, this program very quickly usually runs through a comparison, and all the differences between the files in one directory and the files in another directory are identified in red. And to see the differences, you can just double click on each file, and to go back to the list, you just press the overview, so outline. So double clicking on double clicking, first of all, you can see that 5C is changed. 5C MPI and no MPI are identical, except for the fact that some of the MPI directives are commented out in the no MPI, so we won't bother talking about that one. We'll just look at the MPI one. You can see that, recall that from this Excel file, the switch we were using to turn this on and off is model par, remember, model underscore par, and it was row 16, model par 16. So if we look here, you can see that the first change is that a series of if statements have been altered to include this model par 16 as an element. And basically these are just things to ensure that the code steps into the areas that we want it to step into when this switch is turned on. You can see that mostly these changes are pretty minor, and mostly these are just sort of technical changes that aren't really very interesting. The first thing that is really interesting here is this big block of difference here, and it's quite difficult to see in the red, black on red, but hopefully while you can look at it at any rate in your own time, what this block of code is actually doing is it's feeding in, it's reading in the default values from the base specification, which will then be used as constraints that are fed into the optimizing routine. So here is the optimizing routine, okay, and these default values are all being fed in prior to the model stepping in to actually undertake the optimization. So it steps in here into this routine tm underscore grid underscore cal. So that's, in other words, t minus 1, if you like, grid calculate. And it's already loaded in these default values that we wanted from the base simulation. Now here, this is the you can see this is the subroutine tm underscore grid cal, and this has got a fair few fairly significant changes, and that's because this is where the optimizations are effectively managed. And you can see here there's this big block of code here. Basically the optimized, the initialized values, usually by the model, each time the model comes to optimize at a particular grid coordinate, it reinitializes all of the variables that are treated as outputs, so that if any of these outputs don't change, you can rapidly see which ones they are, because they're all set to this default value -999. So all this is doing is it's avoiding this reinitialization by setting these values up to their values under the default case. And having done that, then the model will run through this stuff here. Again, there are a couple of minor changes, but then you've got this this block of code here, and here is where the routines that are actually conducting the numerical optimization are being fed in the pre-initialized values for consumption and pension participation. And so they feed in here. The model then optimizes at this point here under this continuous choice. Basically, this is the routine that conducts the continuous choice decision. And then there are a bunch of routines that effectively save results. So there's a little bit of change there, and then the final substantive alteration of the code is under this code where you, as I said earlier, that referred to continuous choice. And basically, this is just simply avoiding an optimization over consumption if we are if this flag model underscore par 16 is set to on, in other words, is greater than 1. Here it won't optimize anymore. It will just set the consumption equal to the default consumption and evaluate the value function associated with that. And that's it. There's no other changes. That's all that was required in order to implement this behavioral alternative. And after that, the model's compiled again, and we're ready to project the effects of policy counterfactuals in the next stage of the tutorial.